Let us discuss two regularity conditions which are often assumed for the functions which we are optimizing. So you will see that the performance of many of the algorithms depends on whether these regularity conditions hold or not. And for certain regularity conditions, the performance is actually better. So we start with the notion of smoothness. Right, a function f is said to be smooth, or I should say L smooth, if it satisfies this condition. So it satisfies gradient f of x minus gradient f of y norm is less than equal to L times norm of x minus y. Right, so this is the L smoothness condition for a function f. Obviously f has to be differentiable for smoothness to make sense because gradient is used. So only for differentiable functions we define L smoothness property. If the function f is twice differentiable, then so if it is twice differentiable, then an equivalent condition is that the Hessian of f is less than equal to L times identity. So in the sense that what I mean by here is that Hessian of f minus L times identity is negative semi-definite. Right? So this is another equivalent condition which is perhaps easier to check for functions for them to be smooth. So as a simple example, let us take the function half of x transpose ax plus b transpose x plus c. So let us take this general quadratic form. We already know that its Hessian is given by a. So what is the value of L for which this is less than equal to L times identity? This we already know. The eigenvalues of a are between the minimum eigenvalue and the maximum eigenvalue. So for a to be less than equal to Li, it is required that lambda max of a is less than equal to this number L. Right? So a function is L smooth means that its maximum eigenvalue of a is less than equal to L. In other words, this function is lambda max of a smooth. Right? So for example, if lambda max is 3, then it is 3 smooth. So L value of this parameter L is 3 in that case. So what is the intuitive meaning of smoothness? Smoothness implies another condition which is called the quadratic upper bound. So quadratic upper bound is that f of y is less than equal to f of x plus gradient f of x inner product with y minus x plus L by 2 norm square of y minus x. Right, so this is the quadratic upper bound condition and it is implied from the smoothness. So what does it really mean? Let us draw a simple one-dimensional example just to try to see what quadratic upper bound condition means. So here I have drawn f of y and the dotted line represents this quantity, the quantity on the left. So the left quantity on the left is always, which is a quadratic function of y. So this is a quadratic function of y, right? So this dotted curve is a quadratic function and f of y could be anything. So the dotted curve is always above the function. So this is the quadratic upper bound. So at any point x, we can find such a quadratic upper bound whenever the function f is smooth, L smooth in particular. And in fact, how skewed this quadratic curve is depends on the value of L. Right? And in this also tells us the intuition for smoothness. So the intuition for smoothness is that the gradient of f does not change too abruptly. So if the gradient of f is changing too abruptly, then L will be very high. And the function is L smooth if the gradient of L does not change too abruptly, no more abruptly than the value of L implies. So when L is high, this curve will be very much skewed. It would be something like this. And if L is low, then this curve will be very flat. So the upper bound curve will be very flat, right? And if L is high, it will be very skewed. So that is the intuition behind smoothness. So ideally we want L to be not very high, so the function does not change too abruptly, and in cases when it does not change too abruptly, the optimization algorithms work better. Now that is only one side of the story, and then there is another side of the story, which is strong convexity. So we have already seen the notion of convexity. So if you recall, convexity required that gradient of f was positive semi-definite, right? So that was the requirement for convexity. Now strong convexity, or mu strongly convex. So a function f is mu strongly convex if Hessian of f is more positive definite than mu times identity. So this is the mu strong convexity. Obviously mu is equal to 0 means regular definition for convexity, and for mu greater than 0, this is a more stricter definition, right? It's just more stronger definition, more stronger requirement, right? So such a function is said to be mu strongly convex. Again, let us take an example of the quadratic form. So x transpose ax plus b transpose x plus c. Its Hessian we again know is a. And what is the value of mu for which a is greater than mu times identity? We can see that mu is equal to lambda min of a. So in other words, this function is lambda min of a strongly convex, right? So this function is lambda min of a strongly convex. So mu is lambda min of a in this case. So obviously, as I said, if lambda min of a is 0, we would actually get a linear, we would still get a quadratic function, but it would not be strongly convex, it would just be convex. But if lambda min of a is greater than 0, then it is strongly convex. Now, in general, it holds that L is greater than equal to mu. In general, the smoothness parameter is greater than equal to mu, because as you can see that Hessian of f has to be greater than equal to mu times identity, but it has to be less than equal to L times identity. So in general, L is greater than equal to mu. Very similar to the quadratic upper bound condition we saw, there is a corresponding quadratic lower bound condition. So the quadratic lower bound condition for strongly convex functions is that f of y is greater than equal to, so in this case the function is above its bound, f of x plus gradient f of x comma y minus x plus mu by 2 norm of y minus x square. Now as you may remember, the first two terms appear in the definition for convexity. So if these two terms are there, we have convexity, right? Or equivalently, if mu is equal to 0, we have convexity. So this last term is the extra term. And like if we try to draw it, so this would look something like this. So here again, I have drawn the function f of y, and this blue line is the tangent. So remember, in the case of convexity, we always said that the function is always above the tangent at any point. And the strong convexity is a stronger requirement, which is saying that instead of the tangent, now we have a whole quadratic curve, and the function is above this quadratic curve. So this is the right hand side in this equation, in this inequality. So this is the quadratic lower bound. So in general, for any function, for any convex, strongly convex function and smooth function, we would have both a quadratic lower bound and a quadratic upper bound. So the quadratic lower bound is determined by the second derivative of the quadratic lower bound is mu times identity, and the second derivative of the quadratic upper bound is L times identity. And sandwiched between these two bounds is our function f. So the blue curve here is the quadratic upper bound and the red one is the quadratic lower bound. In general, let me just conclude that in general, algorithms perform better in the sense that they require fewer iterations when L is small and mu is high, right? So L is always greater than or equal to mu. So L is small and mu is high. In other words, we have the so-called condition number for any strongly convex function and smooth function. We have the condition number L by mu, and this should be as small as possible. Obviously, it is always greater than or equal to 1, but in general, it should be as small as possible. If it is very large, say 100, 10,000, then the performance of the algorithm will be generally worse. And if it is smaller, then the algorithm performs better. Now, these are two of the regularity conditions. These are not all. There are various notions. There are other notions also defined similarly, like smoothness of the second derivative and so on. But these are the ones that are most widely used and sort of easier to calculate as compared to the others.